and welcome. In our lesson today, we are going to discuss the Haber process. Now, first things first, before we do that, I want to ask you this. As a student, have you ever been taught any concept or any process in chemistry and you ask yourself, how relevant is this to us? Is it beneficial to me or to any other individual in the world? Now, I get asked such questions a lot by my students. They're like, Madam, why do we need to study these processes? And I always tell them that chemistry is important. We owe a lot of our advancements to chemistry and so on. But in this lesson today, I'm going to actually prove it to you. How? By using the Haber process. Now, the Haber process is one of the most significant breakthroughs in chemistry. Now, we owe a lot of the advancements that we have in the agricultural sector to this process. How? You ask maybe. Now, let me tell you this. Haber process is used in the production of ammonia. Ammonia is necessary for the formation of fertilizers. Do you see where I'm going with this? Fertilizers are one of the main reasons that we are where we are right now in terms of food security. So we owe a lot of the food security we have right now to fertilizers. So indirectly to the Haber process. Now, if you want to take a look at this captivating process, be sure to stay tuned in until the end of the lesson. Now, let us start with this lesson. I want to promise you this. I will try my best to ensure that the lesson is brief but yet comprehensive. And I will make it a point to tackle all the examinable bits, those that are usually tested on. So let us start. So as mentioned before, Haber process involves the industrial manufacture of ammonia gas. So if you want to produce ammonia gas, you're going to need two gases, specifically nitrogen gas and hydrogen gas. Now, where are these two gases obtained from? Nitrogen, of course, is easy. This is simply obtained from the air. The reason is because nitrogen is the main component of air. So the source of nitrogen is fractional distillation of liquid air. What about hydrogen? Hydrogen can be obtained either from natural gas or from cracking of long-chain alkanes. Now, long-chain alkanes are simply alkanes that have a lot of carbon atoms, more than 10. So what happens is that long-chain alkanes tend to have few uses. So they are broken down into short-chain alkanes that have a variety of uses. Now, this process is known as cracking. So cracking usually occurs under very high temperatures and sometimes with the involvement of a catalyst. So if you break down a long chain alkane in order to form a short chain alkane, this process leads to the production of hydrogen gas. So this hydrogen gas can be a source for the hydrogen gas needed for the Haber process. Now, those are the two raw materials and where they are sourced from. The conditions. The next point, of course, is the condition. Now, there are three conditions that need to be present for the Haber process. Number one, presence of a catalyst, specifically iron. Now, iron metal is used as the catalyst for this reaction. A catalyst is a substance that speeds up the rate of a reaction. Most industrial processes use a catalyst. Now, the catalyst that is used is finely divided. You'll find some books mentioning finely divided iron catalyst. What does it mean when it says finely divided? This simply means that the catalyst has been broken down to very, very small particles. And the reason is so as to increase the surface area, therefore speeding up the rate of the reaction. So the catalyst is iron. Moving on to the next two conditions, temperature and pressure. Now let's start with temperature. An optimum temperature of 450 degrees Celsius is used. Now, just FYI, low temperatures will actually be better. That means that if you had low temperatures, there will be a higher yield of ammonia. More ammonia will be produced. Now, in case you're wondering, how does temperature relate to the yield of ammonia? Let me tell you this. If you are a Form 3 student, then this is a topic that is discussed in detail in Form 4, rates of reaction. If you're a candidate, then you should be aware of this. And if you want to remind yourself, I have a video explaining this in further details. Be sure to check it out. Now, coming back to this, low temperatures will actually be preferable for this process. But you find that low temperatures sometimes cause the reactions to be extremely slow. So a compromise is reached whereby temperatures of 450 degrees Celsius are used. Last one, pressure. Now, pressure. Very high pressures will actually be best for this process, because if you have high pressures, then the yield of ammonia, the amount of ammonia produced, will be extremely high, which of course is usually the best. But there's always a but, isn't there? But maintaining high temperatures is extremely expensive, is extremely costly. So this will make the whole process expensive, and the final product will be very costly. Who will want to buy it? So anyways, this is impossible. So a compromise again is reached of temperatures of around 200 atmosphere. So what do you need to know from all of these? You need to know the three conditions: presence of a finely divided ion catalyst, a temperature of 450 degrees, and lastly a pressure of 200 atmosphere. And up to this point, we are now ready to start with the actual process. Now, first thing, nitrogen gas is mixed with hydrogen gas. Now these two form a mixture. Now the ratio at which the two gases are mixed is 1:3. So with every 1 mole of nitrogen gas, you are having 3 moles of hydrogen gas. So a ratio of 1:3. In case you're wondering, why does this ratio need to be as such, then let's take a look at the structure of an ammonia molecule. This is ammonia. Now ammonia has 1 nitrogen atom, but how many hydrogen atoms? 3. So 1 nitrogen atom to 3 hydrogen atoms. So the ratio has to be 1:3. With every 1 mole of nitrogen, you are having 3 moles of hydrogen gas. Now this mixture is then fed into a purifier. Now the name speaks for itself. This is a purifier, so it filters the air. It filters the mixture by removing any dust particles. Now the reason why dust particles have to be removed is, if not, they will end up poisoning the catalyst. This simply means that they will end up damaging the catalyst. And catalysts can be expensive. So if a catalyst is continuously damaged, that means that it will have to be replaced time and time again, which again will make the process costly. So in order to prevent this, the air is filtered in order to remove dust particles. This is done through a process called electrostatic precipitation. Now, 2 things of note there. The air is filtered in order to remove dust particles, which will otherwise poison the catalyst. This is done through a process called electrostatic precipitation. Moving on. Now, what happens in the compressor is that the gases are exposed to very high pressures, as stated before. So 200 atmosphere. How is this attained? By compressing the gases. Now, after this is done, we are moving on to the next step. And that next step is the heat exchanger. So in the heat exchanger, you're going to pre-warm the gases. Preheat the gases. Warm them a little bit before they move to the catalytic chamber. The catalytic chamber, as the name suggests, is where the catalyst is found. So in this chamber, you're going to have the very high temperatures that we mentioned, 450 degrees Celsius. You're going to have the finely divided catalyst. And this is where nitrogen reacts with hydrogen gas, leading to the formation of ammonia. So the equation is as such. Now this reaction is exothermic. That means that it leads to the production of heat energy. Now once the ammonia has been formed, it then passes back into the heat exchanger. Now on its way back, what happens is that it's now cooled a bit. So those are 2 roles of the heat exchanger. Number 1 is that it preheats the gases. Now it preheats the gases on their way to the catalytic chamber. And number 2 is that it cools the ammonia that is formed. So once the ammonia has passed through the heat exchanger, it then moves into the condenser. So the condenser condenses the ammonia gas into liquid state, which is then collected, of course, Now, going back, in the catalytic chamber, not all of the nitrogen will react with the hydrogen to form ammonia. Some of the nitrogen and hydrogen will remain unreacted. So what happens to these two? Now these two pass back into the heat exchanger and they will then be recycled. So they will move back to the catalytic chamber where they will react with one another, leading to the formation of ammonia. Now this is one of the reasons why this process is economical, because the gases that didn't react, the nitrogen and hydrogen, are recycled back. and they react again to form ammonia. Now, this is the Haber process. See how short and simple it is? Now, what I'm going to do at this point is that I'm going to go through it very briefly through the steps involved, just to ensure that content imelala. So point number 1 is the purifier. So the mixture is filtered in order to remove any dust particles that will poison the catalyst. This is done through a process called electrostatic precipitation. Moving on to the next, compressor. So the mixture of gases of nitrogen and hydrogen gas are compressed at very high pressures of around 200 atmospheres. Third step, they are moving into the heat exchanger. What happens in the heat exchanger? The gases are preheated. Next step, catalytic chamber. In the catalytic chamber, the nitrogen reacts with hydrogen to form ammonia. This of course occurs under temperatures of 450 degrees Celsius and in the presence of ion catalyst. Now, any ammonia that is formed moves to the condenser where it's condensed to liquid and tapped and collected. Any unreacted nitrogen and hydrogen is then recycled back. And this is the process. So, what I'll be doing is I'll be discussing a few KCSE questions on the Haber process. So if you feel like you want to test your understanding of this process, then be sure to check it out to see whether the concepts have truly been internalized. I wish you the best and may I see you in the next video.